So good afternoon, everybody. For some historical reason, there has been a little mistake on the title of my talk. I will not talk about optical ptychography, first because I think it's not ambitious enough, and second because I am not an optical ptychography specialist or expert. So I would rather talk about ptychography over all wavelengths. All wavelengths might be a little bit too ambitious. Actually, we will talk about ptychography at the wavelengths where it has been done. Okay, so ptychography at all wavelengths which has been demonstrated so far. So I'm working at Institut Fresnel in Marseille, and I'm working in a group which is called the COMICS team for Coherent Optical Microscopy and X-rays. We are gathering different expertise from various fields. So I'm working with coherent X-ray microscopy. I'm developing an X-ray microscopy method based on coherent diffraction imaging. I'm working a lot with Marc Alain, who is a specialist of inversion problems. He's more a theoretician and a specialist of signal analysis. Patrick Ferrand, who has developed optical ptychography in the group, also together with Marc and myself. And Tilman Grunwald, who is working with incoherent X-ray microscopy, but who has also taken a great part into the development of ptychography these last years. So as you can see, we are gathering our different expertise and different know-how to develop ptychography. Where to start from talking about ptychography? Probably most of you, I guess, you haven't heard the name this word before, I suspect. And if I asked myself where to start from, and unfortunately, maybe, I think the most easiest way to start with is the following one. So it's the equation that explains you everything you have to know about ptychography. So what do we have here? We have rho of R, which is the scattering function that I will call further on the object, which is going to be described as a function of the real space coordinate R. We also have a probe, a finite size probe or a structured illumination, which is centered around several given positions successively. And we have the intensity here, which is our measurement, which is described as a function of the reciprocal space parameter Q. So Q is the Fourier transform of, is the conjugation relation related coordinate of R. And in the formalism of ptychography, what you have is the probe times the object. You take the Fourier transform of it. This is to simulate how the exit field propagates to your detector. And you have a measurement in your detector plane, which is the intensity, that is the square amplitude of the Fourier transform. I will come back again and again and again on this. Don't worry if you do not understand right now everything. So to illustrate a little bit further, here, the sample, rho of R, you see it's here in this case, it's a biomineral. It can be very different kind of sample. This is what I want to image. This is my target, let's say. I illuminate this sample with a finite size probe. In this case, it's a probe resulting from a focusing lens, and it's an X-ray, and the source is an X-ray beam, a synchrotron beam. I focus my probe onto my sample, and I will scan my probe along the Ty and Tx direction, which are two directions which are transverse to the probe direction, okay? And I have to be very careful when I'm translating my sample, where I'm scanning my sample. I have to pay attention to the fact that the steps along the Y and X direction have to be smaller than the probe size. This is a very important condition. I will come back on this condition again. And what I measure, the information I collect, is this one. So it's a two-dimensional intensity coherent diffraction pattern that you measure on the detector plane, which is placed further away from the sample. So you can see that between the sample and the measurement plane, there is no lens, there is no optics. Okay? And ptychography, the aim of ptychography is to solve the inverse problem, meaning I want to solve rho of R, I want to retrieve rho of R from a set of intensity measurement measured in the reciprocal space for different probe positions. So it's a phase retrieval problem. I want to retrieve the phase of the diffracted field and back propagate my diffracted field to get access to the exit field and therefore thereby to the sample. It's okay? It's a phase retrieval problem, and I get the information, the price I have to pay to get this phase retrieval working is that I need to introduce some redundancy in my problem. So I have partially redundant information coming from the fact that when I scad my probe onto my sample, I have two successive probe positions produce an overlap. Okay? So we can write it again and again. So it's a microscopy method which aims at retrieving the sample function from the set of intensity patterns produced by a translational dependent probe. And actually, when you write this, you are opening already a lot of questions. You are raising a lot of questions which are extremely interesting to address. So when we are talking about microscopy, you have to ask yourself what is the spatial resolution, what is the sensitivity you can achieve. When you are talking about the sample function, you have to explain what is the sample function, what is the scattering process, what is the beam-sample interaction. Retrieving means that you need to develop an inversion strategy. What is this inversion strategy? Intensity patterns. So it means that you have to take into account the way the field propagates to the detector, and also how you sample your signal. And also regarding the probe, you can ask yourself, what is the nature of the probe, or what is the probe shape? Okay? So all these questions, I will address some of these questions in my talk, not necessarily in this order. So this is the content of the talk. We will start with the general principle of ptychography, which I have not described yet, where the phase information is encoded and how to retrieve the phase. And then we will start our journey over some wavelengths, so visible light, extreme UV, X-ray beam, and electron beams. And I would like to finish with the question of the spatial resolution, which is a very which is an open question in ptychography and which I think is very interesting. So the general principle of ptychography is illustrated here. It's to start gently. I have a finite-sized probe here in blue, and I have an object here which is composed by two point scatterer separated by a given distance, okay? And in the ptychography approach, what I do is that I'm scanning my probe across my object, I record the intensity pattern, and here on this plot, you will see all the intensity pattern acquired one probe position after the other. So it will allow you to have a feeling of how the information is encoded, okay? Oula, c'est compliqué. Okay. So I do it a second time, and I try to comment together at the same time. So you see that the probe sees one object here, for instance. So here the probe has seen the first object. Here the probe has seen the second object, and in the collection of intensity pattern, this information is very, very well encoded. You can see a strong maxima here and there. And when the probe was exactly in the middle, somewhere here, what you could see, if I can do, what you can see when the probe is in the middle, you see very, very tiny interference fringes, which comes from the fact that the two objects are illuminated together at the same time and they create an interference. Okay? So from the whole series of diffraction pattern, you have a lot of information already encoded. And if you would have illuminated your object with a plane wave illumination, this would be the information you would have, so you can see a lot of information at the same time, which are very difficult to retrieve and to sort out. Okay? We can go a little bit further. We can try to understand how is the information encoded. So again, 2 point scatterers, which are described by different scattering factor f and f prime. My two scatterers are distant by the distance between the two scatterers is 2 times r, and I will write the forward problem with such a probe. So this is my probe. It is much larger than the distances between the two scatterers. Okay. If my probe is illuminating my first scatterer here, I can write that the exit field is the scatterer times the probe multiplied by the scattering power of the first scatterer. I can propagate this exit field to the detector field using Fraunhofer regime to the detector, and I can calculate the intensity that I will collect into my detector. Okay, by using the Fourier transform of this expression. I can do the same for the second probe position, illuminating the second scatterers, which is characterized by f prime. I have exactly the same expression, square modulus of f prime times the probe in minus r1 plus r. And now, when the probe is illuminating the two scatterers, I have something which is slightly more complicated. It's the coherent sum of the two exit field that I propagate to the detector plane. I take the amplitude square of it, and I have this expression where A and B are given here by this. So in red, you have all the unknowns that I want to retrieve in order to know where were my scatterers and what their scattering power was. Okay. And actually, if you look at this term here, you have a cosinus 2 times QR, which is an oscillating function, which is has a very, very strong signature. And from this oscillatory function, you can directly retrieve or get access to the value of R. So by just looking at the oscillation when the two scatterers are illuminating, you get the distance between the two scatterers. And then you introduce the distance between the two scatterers in these two expressions here, and you can get f and f prime. So it's a very simple way to explain you how ptychography is working, but it gives you a little bit of math in order to have a better feeling of what is happening. Of course, in real life or in ptychography life, you don't have only two scatterers. We don't have simple f and f prime. They are complex valued normally. So it's a little bit more difficult. And for this, and this is the reason why ptychography has been could start developing only after the advent of iterative numerical algorithms, which has been presented and proposed by John Rodenburg in 2004 and 2005. There must be a typo here. And demonstrated a little bit further with X-rays. So I would like to explain you how the inversion algorithm works. It's very, very, very simple. So we start here with the sample we want to retrieve, we want to image, which is illuminated by a finite size probe, and you collect your series of diffraction patterns for different positions of the probe onto the sample. Okay? And in order to, so this is your data set, and this is what you get before anything, before doing any inversion. So first you collect your data. Okay, and then you use this inversion algorithm into which you take the first probe position and whatever guess object you may think of. It can be very complex, it can be very simple, it can be a random matrix. Whatever start is okay. You calculate the Fourier transform of the product of this, so you are in the plane of your detector, and you compare the square amplitude of this estimate to your measurement. You replace your amplitude by the experimentally measured amplitude with the square root of the intensity. You keep the phase that you have obtained with your first propagation, and you back propagate your exit field, your field to the probe sample position, and you have a new guess of the object, assuming you know the probe. Okay. And now you go to the second position, x2. And you know that there is a very large overlapping between the two successive positions. So actually, the number of unknowns you are introducing when you are going from x1 to x2 is very small. You are adding only a little number of unknown pixels in your numerical problem. And you do the same, probe times object. You propagate to your detection plane. You compare your estimate to your measurement. And you back propagate, and you have a new guessed object. And you do this for all probe position. And you do this again and again, several times. You have to cycle over probe position again and again. And in principle, you get to the correct value of your object. Yes? So it's a beam that has to present some special, that has to be spatially dependent. So it can be either a focus beam, but it can be a speckle beam. It can be whatever beam. But when you scan your beam, if you use a plane wave, that means all your sample will be illuminated. So shifting a plane wave will not, scanning a plane wave will not introduce any diversity in the problem. So it has to be some structured illumination. As a start, people were thinking about finite sized beam, but now it's much more various. Yeah. Yeah, sure. Yes. So if you know your probe, you can, and in the very simple example I gave here, or illustration I gave here, you can really choose a completely random guess object, like amplitude and phase of the object being random, completely random, and it will work very, very nicely. When you do not know the probe, things start to be a little bit more time-consuming in terms of convergence. So in order to fasten a little bit everything, you usually start with a descent probe. But you can retrieve at the same time the probe and the object without knowing them very well. And it's very, very robust to a random initial start. In this special case, which is simple. Sorry. Yeah, another question. Ouais. Yeah. You need I mean, you can do it in whatever order you want. You don't need to do 1, 2, 3, and so people, for instance, are scanning as spirals, or you can scan randomly, or even if you take into account the fact that we are using piezo, but piezo are not accurate enough, so actually you are not really moving along a mesh, but you are moving along a mesh plus a random position. This doesn't matter, but at least you have to make sure that you have enough redundancy in your dataset. Enough the redundancy, meaning that at the end, if you sum all the energy that you have deposited on your sample, you have to make sure that there is no empty region of null energy, for instance. You understand? So the order is not important. What is important is that there is an overlap, but you are doing the measurement in whatever order you want. Yes. And in the inversion algorithm, I'm not so sure. I think it works better if you are retrieving in a reasonable order. I mean, if you start from here and then you retrieve this part, that part, and that part, you never use the fact that you are overlapping, so it will not help the algorithm. So in terms of efficiency, yes, you have to, again. Okay, so let's have a look at the algorithm at play. So what you will see here, you will see the scan position. This is roughly the size of the probe. This is the intensity, which is measured at the different scan position. And here, you will see the object retrieved, hopefully. Aïe, 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 j'ai du mal avec cette souris. Ah, voilà. Okay. So the scanning position are here. The intensity at each beam position, and here the retrieved object when you take into account all the intensity pattern acquired one position after the other. So you have seen that there was one first cycle, and then I'm cycling again and again to refine my solution. Something I didn't mention here, you can see that the intensity is plotted on a log scale. You do not have a lot of photons actually on your detector. It was on purpose. So this one is quite corrupted by photonic shot noise. Okay? Questions? Okay, I'm fine with questions. Huh? It's a shell. It's a cross section of. Who asked the question? It's a cross section of a shell. So something very important also to keep in mind when we talk about ptychography is the fact that it's you retrieve a complex valued object. So you retrieve your object is a complex value, so it has an amplitude and a phase. And actually, the phase holds all the physics is usually hidden or held by the phase of the object. Okay, and this is what is illustrated here. So it's a 3D X-ray ptychography tomography example. So you don't really need to know what it is to understand to see the beauty of it. You will see. So this is the amplitude, which is a little bit corrupted by noise. And this is the phase that is retrieved together at the same time, okay? So it's a rather big object. And actually, with X-ray, you can write that the phase is related to the path integral of a quantity which is delta R, which is actually the real part of the index of refraction. Okay, delta of R. And actually, you can also make the link between delta of delta and the mass density of the object. Okay, so we are using this. Alors, comment ça va marcher? Okay. Et no. So people are using this to retrieve quantitative information into the object. So you can see, I think here it's a three-dimensional electronic chip of whatever device. And what is very nice is that the color here encode is related to the phase that was retrieved and encode the mass density. And from the mass density, they could discriminate between oxide, capacitor, titanium, aluminium, and tungsten, and so on. So it's a very, very efficient way to get quantitative imaging. Okay? You don't have 50 shades of gray color scale, but you have, but you really have, you really have quantitative information. Okay, so just a few words. So it's a lensless microscopy method. It's a phase retrieval, so we retrieve the phase from intensity information. We use the finite size probe, and we assume that we are in the far field regime. We introduce a lot of redundancy in the measurement. We also assume that we can write that the probe sample interaction is simply a multiplication. We are in the multiplicative regime. And the object that we are retrieving is a complex valued function. So this is what you have remember about ptychography. Yeah? This is a question for the end. because you will have some of your answer. Okay, so now let's start our journey over some wavelengths, and let's start with visible light. Okay? It doesn't mean I don't want question, but this one is particularly relevant a little bit later. That's why. So these are the wavelengths that we will look at if I'm not too slow. So in optics or with visible light, the source is typically a laser beam. The objective of the experiment or the approach is to get quantitative information, but the difficulty that we have to face or to solve is the fact that in optics many materials have an anisotropic behavior. We will also see other sources. So high harmonic generation source, where the beam is polychromatic, and what you want to do is wavefront characterization. With X-ray sources, we have a very limited numerical aperture because we don't have too many photons, but we want to retrieve quantitative 3D information. And with electron beam, you suffer a lot from optical aberration and dynamical effect, And what you want is, of course, to get the best resolution as possible. This is really the target of electron microscopists. So we will go from 10 to the minus 6 meter to 10 to the minus 12 meter. Okay? And these are photons, and these are electrons. Okay? So let's start with optics. So as I mentioned here, briefly, in optics, material is often non-anisotrope. So rho of NP cannot be described by scalar quantity anymore. We need a vectorial approach. So what does it mean? Let's assume that my object is here. It's an object which behaves anisotropically. It means that if I have an illumination which is characterized not only by an amplitude and phase, but by two components corresponding to the polarization state of my field. For instance, here, if I have a linear polarization, when I will go through the sample, the different components of the illumination, Px and Py, will behave differently depending on the orientation of the neutral axis of the object, and the exit field will lose its linear polarization and may become an elliptical field. So the exit field is described by two components, Ex and Ey. The object is described by a 2x2 matrix. This is the Jones matrix formalism, which was introduced in 1941. And the illumination is described by two components. Okay, so I'm not in a scalar regime anymore. I am in a vectorial regime now. And you can use ptychography to solve this problem. You will use, again, a scanning probe across your sample. You will collect all your intensity measurement onto your detector in the far-field regime, exactly what I have said. But in addition, you have to introduce a little bit more information. You have to use a linear polarization to shape the state of your illumination. And you also have to use a linear analyzer to detect the different states of the exit field. And in practice, you only need to use 3 different polarizer position or state and 3 different linear analyzer. So it's a 9x9 measurement times all the position. It has been developed by Patrick Ferrand a lot. In our lab together with Arthur Baroni. So from the Jones matrix, you can get access to the material optical properties, such as the transmission, the optical path length, the effective retardance, the orientation, and the ellipticity. And this is typically the kind of image you retrieve. So the transmission here, which is almost invariant over the sample, on the contrary to the orientation of the axis, which is which has a very specific spatial distribution. The birefringence here, the optical path length here, which is not very spectacular, on the contrary to the retardance, where you can see that the number 2 is birefringent. And in addition to your sample reconstruction, sample retrieval, you can also retrieve the probe profile, so the probe that was used to accumulate your data. And as I said, we are using 3 different kinds of probe, so 1, 2, and 3. And this one corresponds to an horizontally linear polarization, this one a vertically linear polarization, and this one to a polarization inclined by 45 degrees. And you retrieve the amplitude and the phase of the 2 components. And what is very, very nice, maybe it's a little bit upper level information now, but what is very nice is that you have the phase relation between your different components. Okay, so all this information are phase and amplitude, but also relative phase information is known. Okay? So it has allowed us to do some structural characterization of a biomineral. So this one is a pearl oyster from Tahiti. And what we are looking at is this tiny area here, where we can see that actually the border of the shell, the edge of the shell, is composed of little, what is called prisms, little domains, which have different fast axis orientation, or one of orientation of the axis. They have also very specific optical path lengths and some retardance. So this is just an illustration of what you can do with this method. But more than that, with optical ptychography, you can also analyze the light field. Okay, you don't necessarily want to analyze your sample, but sometimes you want to characterize very well a beam, which can be a little bit complicated. And in this case, you are using rather well-known objects, and what you want to retrieve is the beam that illuminates your object. And in this case, you only need to play with the analyzer. And again, you scan your sample across your object, you measure your intensity pattern for a given linear analyzer position, you change the linear analyzer position, you rotate it slightly, you do your measurement again. So to do that, the sample has to be non-birefringent, so optically isotrope. So here it's an absorption sample. Either the light goes through or does not go through. Only 3 positions of the analyzer, and the object is reconstructed and the field is retrieved without a priori knowledge. So both quantities here are retrieved without knowledge. It's a reference-free and robust approach, and it's ideal to image convoluted field that I will illustrate here. So here it's a radial polarization field. It has an inhomogeneous intensity. You can see it here. This is the intensity of this field. It has a weak wavefront curvature. You can see it here and there. And you can also have the polarization state in each position of the field, and this is what is shown here. So you can see the polarization state in each position of your field, and it's for fun. It has been propagated so that you have you can see the beam going through, and you can see how the polarization locally is evolving as a function of time, or when you look your beam going through. Okay. And you can have some closer look to how the polarization behave. So here you have a linearly polarized region, so it's really linearly polarized, while here you can see that actually the polarization is more elliptical. Another very nice example is shown here. It's a phase vortex. Quickly, the movie, maybe. So here, this is the information that was retrieved. Again, how the polarization behaves as a function of the position in your field. The polarization is circular whatsoever. Okay, and the last example is here. So it's a speckle pattern. So the intensity is produced by so the light is scattered by a ceiling film. It's a parafilm. I don't know if you are familiar with this. So it's something which has which is a little bit inhomogeneous at the wavelengths of light. And the illumination is an azimutally polarized beam, and you can see that it produced a speckle, which is a strong distribution of intensity, of maximum of intensity, and in each of these speckles you have polarization that you can analyze, and which is different from one speckle to the other, but which is homogeneous within a speckle. Okay. So this is how to illustrate what you can do with optical ptychography. So we introduced here a vectorial formalism to describe the behavior of optically anisotropic material. We used the Jones matrix to express the probe times object, but from the Jones matrix we could derive the material properties. And we could also use this approach to image polarized convoluted wave fields. They were completely characterized, amplitude, phase, and polarization. Let's go to the next example. So in the extreme UV regime. So here, the result I will show you has been obtained by Stefan Witte in the Netherlands. And what is he's interesting in understanding the spectral behavior of his high harmonic generation source. So from this high harmonic generation source, he has a polychromatic beam. So he cannot write this expression anymore. He has to introduce the fact that the intensity, the one that will be collected on the detector, is actually corresponding to a sum over the different spectral contribution, different wavelengths, the sum of all the p times rho at the different wavelengths. And of course, the probe is a function of the wavelengths, and the object may or may not be a function of the wavelengths. Okay? Questions here? No? So this problem, which is described here, can be solved with ptychography, and it was presented some time ago by John Rodenburg, actually, and Darren Beatty in a paper in 2014. So for this, let's go a little bit into the detail of the experiment. So they have near-infrared focusing beam, which is produced here. And this beam is illuminating gas jet. And the beam gas interaction leads to the production of XUV polychromatic beam. So it's a beam which is not only polychromatic, but which is also composed of a comb of odd orders harmonics. So you can see a typical spectral distribution here, the wavelengths and the intensity of the beam, which is produced by this device. And in order to characterize their probe as a function of the wavelengths, they introduce this wave, what they call the wave field sensor, which is actually an absorption sample made of holes. You see tiny squares here, and in these tiny squares you have a grating with different orientation. And in your detection plane, this is typically the intensity you get. So all the speckles are smeared out because you have multiple wavelengths summing up at the same time on the detector. Okay? In order to retrieve their wavefront, they need a little bit of information. Actually, they need to fix the wavelengths at which they will do the inversion. So for that, they use the grating to have a first approximation or first estimation of their wavelength distribution. And the input of the phase retrieval was actually the red dot here. That is the number of orders they want to take into account and the wavelengths of the different orders. And from this, using ptychography, they could retrieve the wavefront for each of these orders at the wavefront sensor position. And they can also go a little bit further. Actually, if you look at the geometry they are using, the gas jet is placed here slightly before the focusing of the infrared beam. So the gas jet is here. Actually, this gas jet is producing a divergent beam, which apparent focusing would be placed here. And of course, what they want to know is not what is the wave field here in this plane where they have the sample, but they want to know here at the focal plane what is the beam. Okay? So this is what they are doing. They use the wave field they have calculated or retrieved at the sample, and they back propagate it along the path through the focus. Down to the gas jet position, for instance. And this is what they can see for the different wavelengths. And this is the plane in the gas jet position. So what I want to show you here is that you can have multiple wavelengths in your ptychographic problem. And the fact that you are retrieving the probe in amplitude and phase, you can back propagate it at any plane, to any plane you want. Okay? And to doing that, you need to take into account the incoherent intensity signal at the detector plane. So let's go to the X-ray beam. Maybe I should be a little bit faster. So what is very nice with X-ray is that you have a wavelength which is comparable to the interatomic distance. So in this case, we are playing with interatomic distance in crystals, which are periodic stacking of atoms. And we are exploiting what is called the Bragg diffraction. So, for instance, you have here, it's a numerical example. You have here a non-crystalline sample, which is described here. And if you look at the diffracted field of this non-crystalline sample, this is what you will get, except that these are just numerical artifacts here and there. But you will have something which is rather centered around the origin of your reciprocal space, and which decays when you move further away from your origin of the reciprocal space. This is just the Fourier transform of that one. Okay. When you have a crystalline sample, I'm not sure you can see it. Maybe here. You see that actually the sample is decorated or is composed of periodic scatterers. You see the little square here, and the fact that you have little square, or let's say periodic stacking of elements in your sample creates a periodicity in your reciprocal space. So your reciprocal space is not anymore this one, but becomes this one. You see the origin here of the reciprocal space, but you have additional maxima, which are the Bragg peak, the Bragg reflections, which appears here and which directly translate the fact that you have an internal periodicity in your sample. Okay? And doing ptychography with X-ray on a crystals means that you are doing ptychography in the vicinity of a Bragg peak. I will go a little bit, something that I want to show you here, which is interesting, is to get access to one of these Bragg peak here. You see the Bragg peaks, they are not located anymore at the origin of the reciprocal space by definition, they are further away. And in order to get access to them, you have to be a little bit smart with your measurement. You have to make sure that your incident beam and your diffracted beam are placed in a way that Kf minus Ki, so the wave vector transfer, corresponds to one of these Bragg vector. And when you meet this condition, you are in the so-called Bragg diffraction reflection geometry here, for instance. And this is how the construction Ki and Kf behave. And here, at the exit perpendicularly to Kf, you place your two-dimensional detector. Okay, so your two-dimensional detector is here. And it corresponds to a cut through the reciprocal space, which is schematically shown here. And what is very cute with Bragg diffraction is that when you rotate slightly your sample along an axis perpendicular to the beam, you create a little translation of your detector across the Bragg peak. So it's a very smart way to probe in 3D a quantity, because a little angular range of 1 to 2 degrees allows you to span the full three-dimensional information. You do not need to make any tomography approach as you would do in principle for if you would do the measurement in the vicinity of the origin of the reciprocal space in a Ki, Kf geometry such like this one. Okay? So it's a very cute way to scan the three-dimensional space, and very, very efficient. It makes everything a little bit complex because you see that the detection frame is three-dimensional, but the frame is not orthonormal. It's a complex, it's a little bit complicated to handle. It corresponds in real space to a conjugated space, which is also a little bit difficult to handle. I will not go further into these details. I think it might be a little bit too complicated. But what I want you to remember, something which is at the end of this slide, is this one. So when I do the math, actually, I end up with an equation which looks like exactly the same that we have seen so far. So probe times sample, Fourier transforming of it, square modulus of it is proportional to my intensity. But all this information are three-dimensional information. So here I have a three-dimensional probe, a three-dimensional object, and a three-dimensional intensity. And they are linked by a single Fourier transform. Okay, so this is really the beauty of it. You have all the formalism of ptychography that we have seen so far, but you just translate it in 3D. Okay, you also need a little bit of additional math to introduce the strain, which is what people who are doing Bragg diffraction are interested in. So I don't go too much into the detail here, but what you can see is that the expression that we are looking at since the beginning of my talk becomes this one. The object is actually a complex valued electron density object, and the phase of it holds what is called U, the displacement field, which describes by how much the atoms is displaced with respect to a periodic reference system. So from the phase, you get access to U, which is the displacement, and from the displacement, you can get access to a lot of information regarding your material, strain, and orientation. So just for illustrating it, this is the phase which is retrieved in a complex sample we have imaged some times ago. And you can see how the phase behave into this three-dimensional volume. So it's a 3D reconstruction. You can see that some region of very homogeneous phase are very close to region of extremely inhomogeneous phase. And since the algorithm and the method is working very nicely, and from this, you get access to strain, to rotation, and to some other defects that I will not detail too much. So just for you to remember, with Bragg ptychography, we could introduce a three-dimensional formalism, which behaves exactly the same way as the two-dimensional one. Probe and sample are 3D. The material properties could be extracted from the phase of the object. And skip this last point, I didn't mention it. Yeah? No, why? This is not a plane wave, huh? It was there. I erase it. Okay, yes, no, it's the mean Ki. Sorry, you're right. It's the mean Ki that I have drawn. You are totally right. Yeah. Actually, with X-ray, our numerical aperture are typically in the 10 to the minus 2, so our focusing is not super strong. So Ki or the mean of Ki is not very different. But still. So this is the probe at the sample plane, and you can see the probe is typically in the 1 micrometer range, and the resolution we had here is less than 100 nanometer. It's like, I don't know, 50 nanometer. Something. Yes? Yes. So Fourier ptychography, I didn't mention it at all. It's exactly ptychography, but shifted by one Fourier plane. And it's very close to Fourier synthesis, synthèse de Fourier. It's very similar. It's everything that I'm saying here is valid for Fourier ptychography, but you have to shift everything by one Fourier plane. And yeah, and we can, I mean, if you have some specific question, okay. But no, I didn't touch Fourier ptychography in my talk. I agree, yeah. Okay, let's go on. So the last one is electron beam. So electron beam, they have a big problem. Is that the problem they have is that they have a lot of dynamical effects and optical aberration. So they cannot say right that the exit wave is the probe times the object. So this is not valid anymore. So in order to go beyond this problem, they introduce or they use something which was introduced by, who is answering? Normally you should be able to say the name. The only name I'm saying again and again, John Rodenburg. Okay, so the Pope of ptychography. So they are introducing, they are using a method which is called multi-slice ptychography. So the problem is the following. So they are using a highly converging beam to illuminate their sample. So the beam which illuminates the sample is changing a lot across the sample. So this is not such a big problem. This could be solved. But they have also a dynamical effect. So they have multiple scattering from the beam probe interaction. And actually, electron microscopy, really the aim of electron microscopy is resolution. And this is what they can get with different modality, high-resolution transmission electron microscopy. I think this one is annular bright field and angular high-angle dark field. And so with the multi-slice ptychography, what they do is actually they decompose their problem in a series of multiplicative problems. Okay? So they said that their sample, which is rather thick, can be decomposed into a series of planes into which the multiplicative regime will hold. Okay? So they to calculate to make the forward calculation, they have here the probe which illuminates one plane. Probe times this plane interacts. There is an exit wave which is here, which is propagating. The exit wave is propagating to the next plane, and this exit wave is the illumination function of that plane, okay, which interacts with the object, creates a new exit wave, which propagates until the end of the sample, until the last slice, and then the last exit waves propagate to the detector plane, and to back propagate it, they do exactly the same ptychography method, and they decompose their back propagation into a series of planes like this. And this was shown by John Rodenburg in 2012 in optics, and it is used now a lot. It's amazing the development of electron ptychography that is observed and that is going on right now. So here, this is one of the beautiful results that you can find in the literature, but there are many, many very, very nice results. So with this multi-slice approach, they are decomposed their sample in a series of planes. I think here they have more than 50 planes, 60 maybe. And this is the reconstruction they could get. So I don't remember what is the sample. It's a crystal which is composed of different atoms. And they can estimate that the resolution is as good as 15 picometer for a wavelength of 2 picometer. And that most of the broadening they observed in their image is actually coming from thermal fluctuation. So they can image thermal fluctuation in this sample. And they have also, for the same price, a three-dimensional information, of course a little bit degraded along the beam path, but they can see different atoms along the beam path. And with this, I'm almost finishing. So electron microscopy, they need to introduce multi-slice approach to account for multiple scattering events. The three-dimensional information becomes accessible, but they do not do any tomography measurement. And the spatial resolution is strongly improved in electron ptychography. So I think I'm done with my journey through all wavelengths. So we have seen that from this simple approach or expression here, we could go much further into the problems by comparing and playing with different wavelengths. So I hope that the fact that I used multiple many wavelengths in this talk didn't disturb you, but on the contrary, opened some perspective for application into your fields. I hope I was not too confusing. We could see that we could introduce a vectorial approach, for instance, to take into account anisotropy of materials. That in case of polychromatic beam, you can use a multiplexing approach to allow for incoherent information. You can also have directly a three-dimensional formalism instead of a two-dimensional one. And the multi-slice approach was introduced to discuss about dynamical effect. And with this, I am at the last part of my talk, so I can go on or I can stop here, as you want. How much time do I have? 5 minutes is okay. It's very quick. No questions. It didn't blink so far. Yes, okay. But I can stop here. Yes. I stop here. Yes. Acknowledgement. I'm super grateful to all these people. And I had and this one. So before you ask what ptychography means. Thank you.